All right, now we're going to work on a problem that uses the gradient to find the directional derivative. So for example, if we wanted to know how to find the derivative of f equal to natural log x squared plus y squared in direction, that's not how you spell direction. You'd think writing it like 5 times on the last slide would set things up for me. In direction, actually I won't write it that way. I'll do 2 minus 3 at the point 1 minus 3. And actually, I'm even going to erase this f. That way we have to write all the things out. All right, so we're looking for a directional derivative. I know I'm going to need my gradient. So I look for a function, found one, natural log of x squared plus y squared. And I'm going to need grad f for my directional derivative. So I compute my two different components of the gradient vector, df dx, the partial of natural log x squared plus y squared with respect to x, holds on to the x squared plus y squared in the denominator and pulls out the derivative 2x in the numerator. I bet I can cram in df dy right there. Df dy is going to do the exact same thing, but with respect to y. And so my gradient vector is just given by 2x over x squared plus y squared, comma 2y over x squared plus y squared. And then I know that I'm going to be calculating this at the point 1 minus 3. And since this is a little bit messy, I'm going to go ahead and plug that in right now, turn it into a couple of numbers. I'll do it down here. I'll even write what I'm doing. So I know that I care about the point 1 minus 3, so I'm going to evaluate the gradient at the point 1 minus 3. 2 times 1 is 2 over 1 squared plus negative 3 squared, so that's 9 plus 1 is 10. And let's see, 2 times minus 3 is minus 6, again over 10. And I can simplify this to be 1/5 minus 3 over 5. I just simplified out the even terms there. Okay, and then the directional derivative is d sub u f equal to grad f dot u. But I know it needs a unit vector u. So I'm going to look at my vector 2 minus 3. I already know that that's not a unit vector. I could even check it real quick. Magnitude of 2 minus 3 is square root 2 squared plus minus 3 squared. That's square root 9 plus 4, square root 13. So my unit vector u is actually going to be 2 over root 13 minus 3 over root 13. And so my directional derivative is going to be grad f of 1 minus 3 dotted with u. That's going to be 1 over 5 minus 3 over 5 dotted with 2 over root 13 minus 3 over root 13. And that's 2 over 5 root 13, 2 times 1 over 5 times root 13, plus negative 3 times negative 3 over 5 root 13. So those negatives are going to cancel each other out right there. I'll get 2 over 5 root 13 plus 9 over 5 root 13. So that's just 11 over 5 root 13. And that is a number that I don't know the value of, but it is a number. So it's an evaluated derivative at a point, which is what we were trying to do. Kind of trying to interpret this, what we're saying is that if you were standing on the surface of z equal to natural log of x squared plus y squared at the point 1 comma minus 3, and then you started to take 2 steps in the x direction and minus 3 steps in the y direction, the value of z would go up by this much in the very first instant you take that step. That's kind of what a directional derivative is doing.